Swayam Prabha. Digital India. Educated India.
Welcome to the first lesson of the sixth module, which is on stresses in beams part 1. In fact, in the last module we have discussed some aspects of the shear force and bending moment on beams, and in this particular module we are going to discuss that how to utilize those informations on shear force and bending moment in evaluating the stresses in the beam. In fact, today's lessons we will be discussing on the effect of the bending moment on the stresses in a beam. Hence, it is expected that once this particular lesson is completed, one should be able to understand the concept of bending stress in a beam. One should be in a position to derive the bending or the flexural equation. In fact, as we have seen in case of the torsion in a shaft, when we compute the stresses in a shaft or a bar due to twisting moment, we have computed the stresses and thereby we had derived the torsion formula. Now, in the similar line, when a beam is subjected to load and is undergoing bending and shear force, as we have seen, when we will be computing the stresses, we will be deriving the formula which we call as a bending formula, and as we will go along in this lesson we will see how to derive the bending equation. Now, one should be in a position to evaluate bending stress in determinate beams for different loadings. Now, here we are qualifying the beam by saying it is a determinate beam, as you have seen that the beams which we are dealing with, the reactive forces of these particular beams are, we can evaluate the values of the reactive forces based on the equations of equilibrium, and hence they are determinate. And in this particular course, here we are dealing with mainly the determinate systems. Hence, the scope of this particular lesson includes the recapitulation of previous lesson. As we do, we will be discussing the aspects of previous lessons through the question answer session, and we will be deriving the bending or the flexural equation in a beam due to pure bending. In this particular lesson, we will be discussing about the pure bending, and then we will be looking into some examples for evaluation of bending stresses in determinate beams for different loadings. Now, let us look into the questions which were given last time and the answers of them. Now, the first question was on what is the effect of articulation in an indeterminate beam. Now, this is a term wherein we introduce a mechanism in a beam where that particular point, it can sustain the shear force, but it cannot resist any bending moment. Now, if we introduce this kind of articulation in a beam, in an indeterminate beam, then what happens? And the next question, as it has, that if we introduce a similar kind of articulation in a determinate beam, then what is the consequence of that? So, let us look into these two questions in one go, and let me answer those questions. Now, let me start with, say for example, if I have a beam which is fixed at one end and subjected to different kinds of loadings, a uniformly distributed load, a concentrated load, a concentrated moment, and so on. Now, as we have seen, this particular beam, at this end we have a fixed support where we have reactive forces as the vertical force, the horizontal force, and the bending moment. So, this is the reactive force R, horizontal force H, and moment M. and all these three quantities can be evaluated using the equations of statics, namely summation of horizontal forces 0, summation of vertical forces 0, and summation of moment at any point within this beam equals to 0. If we do that, we can evaluate these unknown reactive forces H, M and R. So, this particular system is a determinate system. Now, supposing I introduce one roller at this particular end, and thereby we introduce another reactive force in this particular end. Let us call this as R1 and this as R2. Now, as soon as we do this, this particular beam becomes indeterminate. It is no longer determinate. The reason being that we have 4 unknown reactions which are H, M, R1 and R2. So, there are 4 unknown reactive forces and we have only 3 equations of statics. Hence, this particular system is statically indeterminate. Now, for the solution of this, many times what we do, we introduce another condition in a beam. Let us say that we introduce a hinge in this particular beam inside, and this hinge is such that it cannot resist any moment, but it can support shear force. It can support the shear force at this particular end, but it cannot resist any moment. Now, as soon as we introduce this particular kind of articulation in a beam wherein it cannot resist any moment, that means we generate an additional equation from this particular condition. That means, if we take the moment of all the forces about that particular point, it is expected that the moment resistance will be 0. Hence, we get another equation based on which we can solve the unknown equation, the unknown reactive forces. So, in fact, as you can appreciate now that if you have an articulation introduced in an indeterminate beam where you have one unknown additional unknown reactive forces over and above 3 reactive forces, then we can solve that, or the beam becomes determinate in that situation. Now, this particular articulation can be introduced in this form. If you look into, this is the beam and the other part may be resting on this in this particular form. So, this particular part is fixed at this end, this is on roller. Now, at this particular support, now if you split it into 2 parts, it will be like this, that the reactive force from the top part, from this particular part, this is supported on roller at this end. Now, here we will have a reactive force, and here there will be another, these forces are same. If we call this as R, this is also R, because this particular section can resist the shear force. So, we can have a reactive force generated at this particular end, and in the process you see now this is a determinate system having a fixed end which is a cantilever, and this is like a simply supported one, and these unknown reactive forces can be calculated, which is nothing but the shear at this particular end. Now, if so, for an indeterminate system, if we have an articulation in a beam, then the indeterminate beam becomes a determinate one. The beam becomes determinate because we generate an additional equation. So, we have 4 unknowns, we get 3 equations of statics plus 1 additional equation. So, it becomes a determinate situation. Now, if we have a determinate beam, in which case we do not have this support, it is just a cantilever, then if we have the cantilever beam which is fixed at this particular end, and if we like to introduce this articulation over here, again this is subjected to different kind of loading, distributed loading, the concentrated loading, maybe a concentrated moment. Now, if we have articulation in the beam, that means if we have the beam again in the same form as we were discussing, that you have a fixed end here and this particular part is like this. Now, since this particular part does not have any support, so when it is subjected to the loading, it will topple because it cannot resist any moment over here. So, a determinate beam becomes unstable when an articulation is provided in a determinate system. So, this is the impact of the articulation. One should be careful that if you have an indeterminate beam, if you introduce an articulation within the beam, that indeterminate beam becomes determinate, or you get an additional equation generated for every articulation you induce. And if you have a determinate beam, in that if you introduce any articulation, then it becomes unstable. This is what is indicated over here. The introduction of articulation in an indeterminate beam reduces the beam to a determinate one, and introduction of articulation in a determinate beam reduces the beam to an unstable system. Well, so that answers the first two questions. Now, the third question is, what is the necessity of drawing shear force and bending moment diagrams of beams? Now, you have gone through the previous module, wherein we have discussed various kinds of loading on various kinds of beams, and then we have evaluated the shear force and bending moment at different sections. As you have seen that if we need to know the variation of the shear force or the bending moment along the length of the beam, then if we draw the diagram over the length of the beam, the variation of the shear forces at every section, then it becomes easier to appreciate that which part of the beam is subjected to what kind of shear forces or bending moments. So, from the diagram of shear force or the bending moment, readily we can get the different values of bending moments and shear force along the length of the beam, from which we can say the magnitude of the shear force or the bending moment at which part is larger or the smaller. Hence, as we will be going along for evaluating the stresses in a beam, it becomes much simpler once we know the variation of the shear force and the bending moment in a beam. It becomes easier to compute the corresponding stresses. And in this particular lesson, as we will be discussing, that if you have a bending moment at a section, then what is the consequence of that moment in stresses, or how that induce the bending stress in the beam. So, the shear force and bending moment diagrams indicate the variation of shear force and bending moment respectively in a beam, and it shows the variation of the bending moment and shear force along the length of the beam, and the diagram thus help in finding the maximum values of shear force or the bending moment, because when we will be dealing with the stresses, you will find that we need the maximum magnitude of the bending moment, based on which we will compute the stress. So, that will give us the maximum possible stress. So, we need to know at which point for some loading in a beam the maximum bending moment occurs, and for that reason we need to draw the bending moment diagram, and so is with the shear force. Well, now let us look into that. If a beam is subjected to a pure bending, now you had noticed we had drawn the shear force and bending moment diagram for a beam, say which is simply supported and subjected to two concentrated load, which are placed equally from the two ends, say distance A and A. And in this particular beam, we had drawn the bending moment diagram, wherein you had seen that the bending moment over this particular zone is constant. Now, either of this kind, or if you have a cantilever beam in which you have a concentrated moment, there also everywhere you get the same moment m. So, these are the cases where a beam is subjected to pure bending moment. Now, when a beam is subjected to this kind of pure bending moment, then if we are interested to find out the stresses, we need to develop the relationship between the bending moment that is acting in the beam and the corresponding stress induced in the section in terms of the sectional properties, and that is what we are going to look into now. Now, when we do that, as we made some assumption while deriving the torsion equation, we make some assumptions here as well. Let us assume that this is a beam, part of the prismatic beam, in which the cross section of this particular beam is such that it is symmetrical with respect to the vertical axis y. So, this is y axis. Now, this particular section here is shown in the form of a trapezium, wherein this is symmetrical with respect to y axis, whereas this is not symmetrical with respect to let us call this as z axis, since x is along the length of the member. Now, this is the centroid of this particular section, and the axis which we draw along the centroid, we call that as the axis of the beam. Also, through this plane, along the y axis, if we pass the plane, now along this particular plane the load acts, and also the bending which is acting in the beam there in the vertical plane. So, here we assume that the section is symmetrical with respect to this vertical plane, and the plane of bending is this particular plane, and also in this particular plane the load acts. So, we say generally that the beam has an axial plane of symmetry, which is the xy plane in this particular case, and this is the plane of symmetry. That means, this is the symmetrical, the section is symmetrical with respect to this plane. Also, the applied loads lie in the plane of symmetry. This is what we assume over here. Now, because of the loading, as we have seen that it will be subjected to shear force and bending moment, also it will undergo deformation. Now, when it undergoes deformation, now the axis of the beam which we have chosen over here undergoes bending, and we assume that it does not undergo stretching. And the most important assumption which we make over here is that the plane sections remain plane. That means, the cross section of the beam which was plane before the application of the load and remains plane or perpendicular to the deformed axis after the bending occurs. That means, after the beam undergoes bending, which forms a part of a circle, and the axis also takes that particular form of the circle, and anywhere if we take a section, the cross section remains perpendicular to the deformed axis, and the section which was plane originally remains plane even after bending, and that is one of the assumptions, main assumptions which we make while deriving the bending equation. Now, with these assumptions, if we look into a small segment of this prismatic beam, wherein it is acted on by the pure moment m. Let us say we take a small segment out of this prismatic beam of length dx, and we choose a fiber. Let us call this as A and B, and AB also is of length dx, and let us assume that AB is at a distance of y from this axis of the beam. This is the x axis. So, under loading, let us say it undergoes deformation, and the deformed shape is something like this, which is the part of a great circle. Now, if we concentrate on this particular segment which was originally dx, and let us say that it undergoes deformation, and let us call that along this particular length, this is ds, and this axis of the beam has a radius rho with reference to the center of this great circle. Now, the fiber AB here, this is A dash B dash, let us call it, after deformation. Now, here this was at a distance of y, also undergoes deformation, and let us assume that this particular segment forms an angle d theta. Hence, the radius of this particular arc is equals to rho minus, rho is here and this is y, so this is rho minus y. Now, this particular distance ds from the radius r and this angle d theta, we can write this as rho d theta, and the segmental distance a dash b dash, we can write this as equals to rho minus y d theta. So, the change in the length that occurs, the deformation, if we call this as say du bar, this is equals to the rho minus y d theta, this is the final length, minus the original length which is rho d theta, this is the deformation which is equals to rho d theta gets cancelled. So, this is minus y d theta. Now, if we divide this by original length, so du bar ds is equals to minus y d theta ds, and ds as you know is rho d theta. So, this is nothing but equals to minus y by rho. Now, du bar is the stretching in the curved direction. Now, if we take the horizontal component of that, the angle being very small, the cos of that angle will be is almost equals to 1, and du bar we can call it as the axial stretching du, and likewise the distance ds which is along the arc length, the component of that in the horizontal direction is equals to the original length dx. So, if we substitute that, this gives you the extension du over the original length dx, and as we know, the extension over the original length we have defined that as strain. So, this is nothing but the strain along the axial direction or normal to the cross section. So, we call that as a normal strain. So, normal strain is equals to minus y by rho. So, if we call this as epsilon as the normal strain, this is equals to minus y by rho, and rho is the radius of curvature of the axis of the beam, and many times this particular quantity 1 by rho we designate as kappa, which we call as curvature. So, the strain epsilon is equals to minus y by rho. Consequently, as we know, the relationship between the stress and strain in terms of the modulus of elasticity, sigma is equals to E times epsilon. This is as per the Hooke's law, assuming that we are dealing with the beams which are within its elastic limit. So, within elastic limit, stress is proportional to the strain as per the Hooke's law. So, the stress sigma is equals to E times epsilon, and this is equals to E times minus E times y by rho. So, epsilon is minus y by rho and sigma is minus E y by rho. So, these are the values of the strain and the stresses. These are the normal strain and stress which acts on the cross section of the member. Now, here you note that strain and the stress, they vary along the depth y, which is the depth of the beam. Now, from this particular relationship which we get, they are basically arrived at from the geometrical compatibility of the beam. Under the geometrical deformation, how it undergoes strain. So, this gives us a relationship which we call as compatibility. Now, we will have to look into the equations of equilibrium, so that we can establish the relationship between the stress and the corresponding stress resultant, which is the moment. Now, here if we look into the equations for equilibrium, now let us keep these aspects in mind, that epsilon is equals to minus y by rho and sigma is equals to minus E y by rho, and we need to locate that where along the depth the variation of y is. Now, here we look into a segment of this beam again, and if we look into that, we have shown three axes, the z axis, the y axis and the x axis. Now, we consider a small element here having area say dA. Now, as we know that summation of the horizontal forces Fx is equals to 0, and this force is nothing but the stress multiplied by the area. Now, this if we integrate over the entire area, this is equals to 0. Now, sigma, as we have seen, is equals to minus E y by rho times dA, integral this over area is equals to 0. If we take out these two constant, E minus E rho, E by rho, so this over area A, y dA is equals to 0. Now, we can write this as say as A y bar times this constant value E by rho, this is equals to 0. Now, this means that since area A cannot be equals to 0, so y bar is equals to 0. Now, the meaning of y bar equals to 0 is the distance of that segmental area with respect to the centroidal axis or the origin is equals to 0. That means, and this can happen if the centroid of the cross section matches with the origin, then only the y bar of the whole area is equals to 0. Now, this signifies that the z axis must pass through the centroid of the beam. And also, if we look into if this y equals to 0, then from the expression of strain which we had as minus y by rho and sigma as minus E y by rho. Now, these quantities both strain and the stress when y equals to 0 is 0, that means at this particular point the strain and the stress is 0, and that is the reason this particular axis is termed as the neutral axis. So, in fact, if we look into the cross section, we have a point where the strain and the stress is 0 and it linearly varies in the entire depth of the beam. So, we will have a variation something like this, wherein we will have a 0 strain or 0 stress over here, and here we will have strain and corresponding stresses, here we will have the strain and the corresponding stresses. So, this will give us the variation of the strain and the stress. So, this is one equation of equilibrium from which we can position or we can locate the neutral axis in the cross section. So, for positioning the neutral axis in the cross section, that should pass through the centroid of the cross section. So, given a cross section which is symmetrical with respect to y axis, we got to locate its centroidal point, and through the centroidal point the neutral axis will pass through. This is the information which we get corresponding to this particular equilibrium equation. Now, let us look into the relationship between the moment and the stress. Now, the other equilibrium equation which we can have is the moment value. Now, if we take the moment of this particular area, now this is the beam segment which we are assuming having a moment here which is m, and here we are considering the force which is sigma x times dA. So, the moment of this force is sigma x dA times the distance y. If we call this distance as y, then moment m plus sigma x dA y integrated over the area, this is equals to 0. Now, if we substitute for the value of sigma, this is m minus E by rho times y dA y, this equals to 0. Now, this is nothing but equals to m is equals to E by rho times integral y square dA. Now, as you know, this integral y square dA is the second moment of this segmental area with reference to this neutral axis, and this we designate as the moment of inertia, and we call this as I. So, from this relationship we get m as equals to E I over rho. Now, we have already observed that the relationship between the stress and the rho, we have sigma is equals to minus E y by rho. So, from this we can say that sigma by y is equals to E by rho. So, sigma by y is equals to minus E by rho, and E by rho is equals to m by EI. So, this is minus m by I. So, we can write that m by I is equals to E by rho is equals to minus sigma by y. So, this particular equation which relates the moment with the stress, moment with the curvature, or we call this as the bending equation or the moment equation. Now, this is the equation, this is the diagram now finally which we get for the segment of the beam, as we have seen that this is the plane of bending along which the load acts. Now, this particular axis along which the stress is 0, we call that as neutral axis, and for each cross section if we plot this neutral axis, we will get a surface which we call as a neutral surface, and this is the neutral surface of the beam which is plotted over here. So, this is the axis of the beam and this is the neutral axis of the cross section. Now, the bending equation which we get is of this kind, where the m is the bending moment, I is the moment of inertia, E is the modulus of elasticity, rho is the radius of curvature of the neutral axis, and y sigma is the stress and y is the point at the point where we are trying to find out the bending stress. Now, in a beam at a particular cross section, if we are interested to evaluate the bending stress, so location of that particular point with reference to the neutral axis will be known, and hence the distance y will be known. I is the moment of inertia of the cross section with respect to the neutral axis, and m is the bending moment which is acting at that particular section. So, once we know these parameters, we can compute the value sigma. So, from this we can write that the relationship m by I is equals to minus sigma by y, or sigma is equals to minus m y by I. Now, if you remember that we had considered bending in a beam, say for example, if we take the segment, the positive bending moment in the beam was like this, wherein this particular type of moment causes compression at the top and tension at the bottom. Now, because of the bending which is acting in this particular segment, the bottom fibers undergo stretching, which we call as a tensile, and the top fiber undergoes compression, which is compressive. Now, the positive bending moment, if we apply in this particular equation, we get the stress as negative, and the negative stress indicates that it is compression. And likewise, if we compute the stress at the bottom fiber wherein y will be negative, thereby stress we will get as positive, and thereby the positive stress gives us the tensile stress. So, if we take the positive moment and correspondingly if we place the values of y according to the position of the point where we are evaluating the stress, now the negative value of the stress will give us the compressive stress and the positive value will give us the tensile stress. Well, then these are the steps, as you can visualize now, that if we are interested to find out the bending stress at a point in a given cross section, then what are the steps we should go through so that we can evaluate the stress. Now, as you can appreciate that the point where we are interested to find out the stress, at that particular section we must know what is the value of the bending moment it is subjected to because of the external load that is acting on the beam. So, for a particular type of a beam for which we know the support conditions and the loading on the beam, we compute the value of the bending moment at a particular section where we are interested to evaluate the bending stress. Once we know the value of the bending moment, then for that particular cross section we will have to establish the position of the neutral axis, and once you know the neutral axis, then we can compute the moment of inertia of that particular section and also the position of the point with respect to the neutral axis, the distance y. So, we know the bending moment, we know the distance y, we know the moment of inertia of the cross section with respect to the neutral axis. So, we can compute the value of the bending stress, which is my by I, and this is what is indicated over here, that you got to evaluate bending moment at the point where you are interested to find out the stress. You got to locate the position of the neutral axis, you will have to determine the moment of inertia of the cross section about neutral axis, and you will have to determine the y coordinate of the point so that you know the distance y. So, this is y, this will give us I, and the position of the neutral axis will guide us to evaluate I and y. So, these two parameters will be dependent on this, and once you know this, then we will have to compute the bending stress from this expression, which is my by I. Now, here we can take the appropriate sign of the corresponding parameters and the stress can be computed from this, and we can conclude that whether that is a compressive stress or tensile stress that is acting at that particular point. And that is how now you can visualize that how the variation of the bending moment or shear force along the length of beam is going to help us to evaluate the stress at a point in a beam which is subjected to some kinds of loading. Now, let us look into some examples wherein we can apply this technique. Now, this is the example problem which in fact I had given you last time and I had asked you to solve. Now, let me just tell you the salient point of this. Now, what we need to do is that we will have to draw the shear force and bending moment diagram for this particular beam. and as you can see here, this is on hinge support and this is on a roller support, and there is an overhang on this beam, and this is subjected to uniformly distributed load of 10 kilonewton per meter. Now, here the reactive forces will be, we will have a vertical reaction Ra and we will have the horizontal reaction Ha, and here we will have the vertical reaction Rb, and since we do not have any horizontal load on this, so summation of horizontal forces equals to 0 will give us that the reactive force Ha is equals to 0. Now, summation of vertical force is 0, that means Ra plus Rb is equals to the total force, which is 10 kilonewton per meter over a length of 3 meters. So, this is 30 kilonewton. And now, if we take the moment of all the forces, say with respect to B, then we can get the value of the reactive force R. So, Ra into 2, which is a clockwise moment, and this loading causes an anticlockwise moment, and this part of the loading causes a clockwise moment. So, Ra into 2 plus this part is 10 into 1 into half is the moment about this point, and this part is, so minus 10 into 2 into 1, this is equals to 0. So, this is 10 into 2 20 and this is 5. So, minus 15. So, Ra is equals to 7.5 kilonewton, and correspondingly from this Rb is equals to 30 kilonewton. Now, let us draw the shear force and the bending moment diagram. Now, here we have plotted this, you can have a look at it. So, Ra plus Rb equals to 30 kilonewton, and if we take the moment, as we have seen that Ra is equals to 7.5 kilonewton and Rb is equals to 22.5 kilonewton. Now, let us take a section here at a distance of x, so that we can draw the free body of that particular part. So, if we draw the free body of that part, we have the reactive force Ra, here we have the shear force B and the bending moment M, and the uniformly distributed load which is acting over this particular segment, and the length of this segment is x. So, if we take the equilibrium of the vertical forces, then we have V plus Ra minus 10 into x, this equals to 0. So, this gives us V equals to 10x minus Ra, Ra equals to 7.5. So, this is the expression which we get, V is equals to 10x minus 7.5, and correspondingly if we calculate the value of the bending moment, we have bending moment M, which is acting in an anticlockwise direction. The load gives a moment in an anticlockwise direction if we take the moment with respect to this point. So, M plus 10, this is x and this distance is x by 2. So, x square by 2 minus Ra into x, this is equals to 0. So, this gives us M as equals to Ra into x, Ra is 7.5. So, 7.5 into x minus 5x square. So, this is the expression for the bending moment which is indicated over here. So, we have the values of bending moment and the shear force indicated by this expression. Now, so this gives us the variation of the bending moment and the shear force. Now, as we go along, when x is equals to 0, the value of the shear force is minus 7.5, which is indicated over here. Now, if we like to find out the shear force at the point B, where x is equals to 2, since we do not have any load in between. So, at x equals to 2, the value of V is equals to 10 into 2 minus 7.5, which is 20 minus 7.5, this is 12.5, and this is plus 12.5. Now, you noted that when x is equals to 0, V is equals to minus 7.5, and when V at x equals to 2, V is equals to plus 12.5. So, it varies from minus 7.5 to 12.5. So, somewhere in between the shear force will be equals to 0. Now, if we like to know the position of the 0 shear force, if we like to find out the point where shear force equals to 0, now since we know that this is the expression for the shear force between A and B, so we substitute for V as equals to 0. So, 0 is equals to 10x minus 7.5. This gives us the value of x, which is equals to 0.75. So, at a distance of 0.75 from the left end, the value of the shear force is equals to 0, which is indicated over here. Now, at the point of this 0 shear force, as we have seen earlier, that the possible places where the bending moment can be maximum, they are the points where the shear force is 0, or you can have the sign changes from the positive to the negative or the vice versa. These are the places where you expect that the bending moment is going to be 0. So, here this is one of the place where I expected that the bending moment could be maximum. Now, corresponding to the, so from 7.5 to 12.5 we get over here. Now, if you look into a section corresponding to this beyond this reactive value, then what is the value of the shear force we get? Now, there the section, the free body diagram is something like this, that we have RA here, we have RB here, we have the uniformly distributed load. Now, this is the section which is at a distance of x from here, and we have the section which is V and the moment M. So, V plus RA plus this is RB minus this is 10 times x, this is equals to 0. So, shear force V is equals to 10 x minus RA minus RB. Now, here x is 2, so this is 20, 20 minus RA, RA is 7.5, so this is 12.5, and RB is 22, 22.5, so this is 10. We get a positive value of shear as 10. So, from 12.5 positive 12.5 to negative 10 it comes, and then again here it becomes 0. So, this is the variation of the shear force, and this is the shear force diagram for this particular beam. Now, consequently, if we look into the value of the bending moment, now when x is equals to 0, the moment is equals to 0, and this is what is reflected over here. Now, when x is equals to 0.75, we get a value of bending moment which is equals to 2.813 kilonewton meter. If we substitute the value of x equals to 0.75, we get this is the bending moment. Now, this is the value of the maximum positive bending moment. Now, when we compute the bending moment at this particular point, when x is equals to 2, we find that this is 15 minus 2 square is 4 times 5, 20, and this is 15. So, this gives us a negative of 5 kilonewton meter. So, at this point we get a bending moment which is equals to 5 kilonewton meter, which is negative. Now, as you can see from these two values that this is maximum. Now, this is maximum negative moment and this is the maximum positive moment. So, in a beam, as we have discussed earlier, that you can get the values positive, the maximum values at different points, but if we are interested in the maximum possible values, then whether it is negative or positive, the maximum bending moment that is occurring in this particular section or in this particular beam is 5 kilonewton meter. So, and the maximum positive bending moment, if we are talking about, that is 2.813 kilonewton meter. So, this is the variation of the bending moment and this is the variation of the shear force. Now, if you notice here that the bending moment diagram also changes its signs from positive to the negative. So, somewhere within this particular zone AB, the bending moment is equals to 0. Now, if we like to compute the distance, that we can compute from this bending moment expression. Now, here we have the expression for the bending moment as m is equals to 7.5 x minus 5 x square. Now, if we set this moment equals to 0, we have 7.5 x is equals to 5 x square. So, if we say x as equals to 1.5 meter. So, at a distance of 1.5 meter, the bending moment is equals to 0. So, this distance is 1.5 meter from here. So, the magnitude of bending moment at this point, which is at the support point, is equals to 5 kilonewton meter because of this overhang, and the positive bending moment is this much, and the bending moment is 0 at a distance of 1.5 meter from the left support. So, these are the values of the bending moment and shear force for this particular problem. Now, let us look into this another example, which in fact I had given you last time, wherein in this particular beam we have an articulation introduced, and if you look into this particular beam is of indeterminate type. Now, here this beam is on hinge support, on this it is on roller support, and this is also on roller support. Now, if we look into the reactive forces, here we have the vertical force, here you have the horizontal force, here you have the vertical force, and here you have the vertical force. So, this is RB, this is RC, and this is RE. Now, here you have a horizontal force HA. Now, if you look into the number of unknowns 1, 2, 3, 4, and as we have seen that we have 3 equations of statics and we have 4 unknown reactive values, hence we cannot solve it using equations of statics alone. So, it is an example of indeterminate beam. Now, since we have one additional equation to be an additional unknown to be evaluated, so we need at least another equation, so that we can solve for the unknown reactive forces. Now, this additional equation can be generated from the criteria that it has been indicated that the beam has an articulation wherein this articulation can take the shear, but cannot resist bending moment. So, if we take the moment of all the forces with respect to this particular point as 0, then we get an additional set of equation. So, basically here there are 2 beams which are interconnected at this particular part. So, if we compute the value of the reactive forces, then we can evaluate the shear force diagram, based on which we can find out the maximum shear force in the beam. Now, this is what is the diagram plotted, but you see that this particular beam has been split at the articulation, and we have introduced one reactive force RD over here. Now, these 2 forces, please note here, they are balancing in nature. That means, one beam is getting supported over the other and transferring the shear force here. So, it can resist the shear force, but it rotates when it comes for the bending. Now, if we are interested to find out the values of this, now the uniformly distributed load that is acting over here is Q, this is a length 2L, and all these segmental lengths are L. Now, summation of horizontal force 0 gives you the horizontal component equals to 0. Now, summation of vertical forces, now if we take this particular part, now RD plus RE, this is equals to twice QL, Q times 2L. So, this is one equation. Now, from this we can say that if we take the moment of this RE with respect to this point, then RE into twice L is equals to, this is anticlockwise and this is clockwise. So, this is equals to Q into 2L into L. So, 2L gets cut off. So, RE is equals to Q times L, and thereby RD is equals to Q times L. So, the values of the reactive forces RE and RD equals to Q times L. Now, the left segment, if you take the summation of vertical forces 0, will give you RB plus RC plus, since it is in the opposite direction. So, this is negative. So, minus RD, and P also in the same direction. So, plus P, this is equals to 0. So, this gives us that RB plus RC, this is equals to RD minus P, and RD we have seen as equals to QL. So, this is QL minus P. Now, if you take the moment of all the forces with respect to this, then you get another set of equation for RB and RC, and correspondingly we get the value of RB as equals to minus twice P minus QL, and the value of RC correspondingly we get as 2 QL plus P. So, these are the values of reactive forces. This is RB, this is RC, RE is equals to QL, and the shear force which acts in the articulation is equals to RD, which is equals to QL. Now, if you plot the shear force, now if you take a free body over here, here we have the force P. So, here we have P, this is V. So, V plus P equals to 0. So, V is equals to minus P. So, here we have minus P from here to here, since you do not have any other load. Now, at this particular point, if you take the free body, we have the force which is acting over there, which is P, and we have the reactive force RB. So, we have P, we have RB, and we have V here. So, V plus P plus RB, this is equals to 0. So, V is equals to minus P minus RB, and RB is equals to minus 2P minus QL. So, this is plus twice P plus QL. So, that gives us a value of P plus QL. So, here we get a shear force of magnitude P plus QL. So, from minus P it changes over to plus P plus QL. Then up to this segment, again just before this reactive force, the situation is same, and everywhere we have the identical shear force. Now, immediately after this particular reactive force, if we compute, if we take the free body diagram of this particular part, now we have V plus RB plus RC plus P equals to 0, and from there if we compute the value of V, we find that it becomes again negative QL. So, up to this again it is uniform, since we do not have any load in between, and from QL here it varies Q per unit length over a length of twice L, and so minus QL goes to plus QL, and here it comes back over here. So, this is the variation of the shear force over the entire length of the beam. Now, here if you note that this is the maximum value of the shear force that we get anywhere within this. Here it is P, here it is QL, here it is QL, here it is P plus QL. So, the maximum value of the shear force is P plus QL, which occurs just after this particular reactive force B, and this is what was asked for in this particular example. Now, let us look into this example, which is based on today's discussion, that in this particular beam, let us call this as AB, and this beam has a rectangular cross section of size 50 millimeter by 80 millimeter rectangular cross section. Now, what we need to do is that we will have to determine the magnitude and location of the maximum bending stress in the beam. So, first we will have to find out the magnitude, and also we will have to locate where this maximum stress is occurring, and this is subjected to a concentrated load 2 kilonewton and a concentrated moment 5 kilonewton meter. Now, as I have told you, to evaluate the value of bending stress at a point, what we need to know is the bending moment that is acting at that particular section. So, first we need to draw the shear force and the bending moment diagram of this particular beam. Now, since this is hinge support and this is roller support, here we have a reactive force which is vertical reaction RA and the horizontal reaction HA. We have the vertical reactive force RB over here. Now, if we take summation of horizontal forces equals to 0, we have HA is equals to 0. Now, summation of vertical forces 0 will give RA plus RB equals to 2, and if we take the moment about this particular point of all the forces, we get the values of RA. So, let us compute first the reactive forces and then plot the shear force diagram, so that we can compute the position of the maximum bending moment and we can compute the bending stress. So, this is the reactive force RA, the horizontal force HA, and the vertical reactive force RB over the beam segment AB. Now, if we take the moment about B is equals to 0, gives us that RA into 3, which is a clockwise moment, and plus 5 kilonewton meter, which is also a clockwise moment. 2 kilonewton meter gives anti-clockwise, so 2 into 1, so this is equals to 0. So, this gives us a value of RA as equals to minus 1 kilonewton, and as we have seen that RA plus RB, this is equals to 2 kilonewton and RA is minus 1 kilonewton. So, this will give us a value of RB as equals to 3 kilonewton. So, these are the values of RA and RB. Now, if you take a section over here, a segment which is having a reactive force and there are no moments. So, the shear is equals to the reactive force, which is equals to 1 kilonewton, and this is being negative. So, this is in the opposite direction. So, this is a positive value of the shear, and as we have seen, the moment does not change the vertical force. So, uniformly we have the uniform shear which is of plus 1 kilonewton. Now, at the load point there is a changeover from minus 1 plus 1 to the minus 3. So, this is a 3 kilonewton load which is shear which is acting, and then finally again it is constant over this particular region. So, this is the value, this is the diagram which is the shear force diagram. Now, if we plot the bending moment diagram correspondingly, we find that at the point of concentrated moment from 1 kilonewton meter it changes over to 4 kilonewton meter, and here the moment comes to 3 kilonewton meter, and here it is 0. So, this is the variation of the bending moment diagram. Now, as we can see, the value of the maximum bending moment is equal to 4 kilonewton meter, and as we know, if we compute the bending stress, that stress sigma is equals to my by I. So, sigma is equals to my by I. Now, here m is equals to 4 kilonewton meter, which is 4 into 10 to the power 6, y is 50 by 80, y is 40, and this is 50 into 80 cube by 12. So, this if you compute comes the stress as 75 megapascal, and this bending stress here is a positive value. So, because of this we will have compression at the top and the tensile stress at the bottom. So, this bending causes a bending stress of 75 MPa, which is located just right of the concentrated moment, and we have a magnitude of negative, which is a compressive stress at the top and a tensile stress at the bottom. Well, we have another example problem wherein we have a uniformly distributed load and a concentrated load on a simply supported beam. We will have to determine the largest allowable value of P if the bending stress is limited to 10 megapascal. This problem is set for you. We will discuss this in the next class. Well, to summarize then, in this particular lesson we have included this, that we have looked into the previous lessons aspects. We have given or introduced the concept for the bending stress, and we have derived the bending equation, and also we have looked into some examples to evaluate the bending stresses in a beam. Now, these are the following questions given for you. What are the assumptions made in evaluating bending stress in a beam? What is the bending equation, and how do you locate neutral axis in a given cross section of a beam? We will give you the answers for these questions in the next lesson. Thank you very much. Welcome to the second lesson of the sixth module, which is on stresses in beams part 2. In fact, in the last lesson of this particular module, we have discussed the effect of the bending and consequently the stresses in a beam due to bending, and we have seen that how to evaluate stress at any point due to the loads which are acting on the beam, and consequently if it is acted on by pure bending, then what will be the stresses. Now, which we have defined as the bending equation or the flexure equation. Now, we will be looking into some more aspects of the bending stresses if they act on a section which is symmetrical with respect to the vertical axis, but could be unsymmetrical with respect to horizontal x axis or z axis, which we have defined. Let us look into then that once this particular lesson is completed, one should be able to understand the effect of bending stress in beams of different cross section which are symmetrical about vertical axis, but could be unsymmetrical with respect to the horizontal axis. One should be able to understand the concept of economical section. Now, we will look into the sections which are more appropriate when they will be subjected to bending, which we can call as most economical.